everyone, this is Data at 622 final project presentation from Group 1. Diego Correa, Aman Darcy, myself Soma Ghosh and Athena Karim. For our final project, we picked the Communities and Crime dataset, which is a dataset we picked from University of California Irvine's Machine Learning Repository. The dataset comprises, it's a normalized dataset, and it comprises of various socioeconomic, environmental, and demographic characteristics, and what kind of correlation we can derive that all these characteristics or attributes have on violent crimes per population, which is the target variable in this dataset. Review of the dataset, as we can see, there are a lot of question marks and data quality issues that we have to deal with. We did a quick descriptive statistics summary, and then we dived into missing value analysis. As you can see, there are close to 22 variables with 84% of the records missing value. So definitely those are the variables we quickly removed from our data set, and that kind of brought us down to 102 variables out of 128 variables that we started with. Then we did a quick and started with an exploratory data analysis of violent crimes. We kind of calculated the top 5 states. DC kind of tops the chart in terms of average crime rate, and we did a quick map of such average crime rate. And then we also looked at the black population, because there is a belief that there are areas of our part of our country where there are higher number of black population. Maybe it has some correlation with the high crime rate, violent crime rate. And if we look at the top 5, DC kind of tops the chart in terms of black population. So on the surface, it looks like yes, there could be some correlation between the percentage of black population with the crime rate. We also did a word cloud of most dangerous communities, and you can see like Camden City and Atlantic City, New Jersey, kind of showed up, along with Baltimore, which is also known for a high crime rate. We are dealing with a lot of variables in this data set, so we quickly decided to look at variables which has less than 25% of correlation against the target variable violent crimes. We quickly removed those variables. We also did a quick check of multicollinearity and those variable pairs. We used VIF score to kind of eliminate one of these variables which have high degree of multicollinearity. Quickly did a set of correlation plots to kind of identify what are the variables which has influence on the crime rate, violent crime rate. And no surprises, like African American percentage of population, definitely that came out as a high influencer, along with people percentage of population living under the poverty line, kids born to never married. Those are some of the important variables that we saw that could have a high degree of influence.
For linear regression model, here I did the ridge and lasso. The gamut package allows us to perform both the ridge and lasso regression models. The library requires the response variable to be a vector and the predictor variables to be a class of a data matrix. Model 1. Ridge regression is a model used when the number of predictor variables in a set exceeds the number of observations, or when a data set suffers from multicollinearity. According to stats, with ridge regression, often predictor variables used in a regression are highly correlated. When they are, the regression coefficient of any one variable can depend on which other predictor variables are included in the model and which ones are left out. Now we'll use the GlamNet function to find the ridge regression model and specify alpha equals 0. Here, this is the code that is used. To identify what a value to use for lambda, we could plot the function using our model fit.ridge lambda.min. But below, we'll use the s equals lambda.min argument to save time. To graph will show below after all models. Here is the train coefficient numbers calculated, and here's another code and the test coefficient for this one. As we can see below, the train and test coefficients are 0.77 and negative 0.364. Now we'll go on to model 2, lasso regression, least absolute shrinkage, and selection operator. According to statistics howto.com, lasso regression is a type of linear regression that uses shrink, which shrinks data points towards a central point, such as the mean. Now we use the GLAMIT function to fit the lasso regression model and specify alpha equals 1. We'll specify s equals lambda.min to find the best lambda. So over here we use this code. Here's the train coefficient, also the test coefficient. As we can see below, the train and test coefficients are 0.83 and negative 0.24. For the next model, model 3, elastic net regression is an extension of linear regression that will add regularization penalties to the loss function during training. Here's the code that was used. Train coefficient was 0.8185317, and for the test coefficient it was negative 0.2584772. Here we plot the MSE. So for the first one, it's plotted is the mean squared error for the lasso. Second one was the mean squared error for the ridge. And finally, the mean squared error was for the elastic net regression. Thank you.
I'll be going over the nonlinear regression model portion of our project. Nonlinear regression models do not follow the y equals ax plus b approach. It allows for flexibility in the model to fit nonlinear trends in data. We'll go over 4 examples of nonlinear regression models. They are neural networks, k-nearest neighbors, support vector machines, and multivariate adaptive regression spline. First, neural networks. Neural networks are regression techniques inspired by theories of how the brain works, or how neurons signal to one another. The outcome is modeled by an input layer and an intermediary set of unobserved values known as hidden units. They are made up of linear combinations of the original predictors. The parameters used in the model include number of hidden units, decay, number of iterations to find parameter estimates, and the number of parameters used by the model. Here we run an average neural network with 5 hidden units. After our model runs, we look at the variable importance. Here you can see that the model creates new variables from the first layer and the hidden units in the model. We next predict on our test data with our neural network model and store the prediction performance for later analysis. Our next model is k-nearest neighbors. The KNN model predicts a new sample of regression using the k closest data points from the training set. The method uses the Euclidean distance, or the straight line distance between samples. Below you can see the Euclidean distance formula. We use the train function, the carrot package, and use the KNN method to perform our model. After our model runs, we can see that the final value used for the model is k equals 13, with an r squared of 0.63. We can visualize this with this plot, and you can see that at 13 we have our lowest root mean squared error. We next look at the variable importance of the model. Here you can see that PCTILLEG, or percentage of kids born of illegitimate parents, have the highest variable importance, followed by 2 different family variables. We next look at our prediction performance. We predict on our test data and store the prediction performance in a variable for later analysis. Our next model we look at is support vector machines. SVM regression models try to find a regression line where each data point is within a threshold. The error is a parameter of the model, and it will then try to minimize the coefficients used in the model. This allows the model to eliminate features and have greater interpretability. We again use the carrot package and apply a radial SVM model. This method will allow the model to find trends in the data set. We then run our model and see we have a r squared of 0.636. Next we look at the variable importance, and likewise to the KNN model, we see that PCTILLEG has the highest variable importance, followed by 2 other family variables. We then predict on our test data set with the SVM model we just generated. We then store the prediction performance in a variable for later analysis. Our last nonlinear regression model we use is the multivariate adaptive regression splines. The MARS model finds not to determine piecewise linear model where each new feature models are modeled in isolated portion of the data. The predicted cut point combination that has the smallest error is used for the model in an iterative process until a stopping point is reached. We'll use the Earth package to generate the MARS model. After the MARS model runs, we see we have a r squared of 0.69. We can visualize our MARS model by using the plotMo function. Here we can see that the model uses 10 predictors in a piecewise fashion. We then look at variable importance. We see that we have a different highest variable importance with PCT kids to PAR, which is percentage of kids with 2 parents that's having the highest variable importance. Next, we predict on our test data and store the prediction performance in a variable for later analysis.
Now we're going to use tree-based methods to predict the number of violent crimes per population for our communities and crime dataset. We're going to look at decision trees and random forests. Decision trees are a type of supervised machine learning method where the data is continuously split according to a certain parameter. The tree can be explained by two entities, namely decision nodes and leaves. The leaves are the decisions or the final outcomes, and the decision nodes are where the data is split. Since our target variable is continuous, we will be building a regression tree. So we have our first regression tree here. It seems like by default, our tree picked the best number of features to use for this tree, and we can also see that it uses the person of kids born to parents who were never married as the feature to split. This is maybe easier to create homogeneous groups with this feature. We have some of the details of our initial decision tree over here. So like I said, by default, our tree already picked the best features, but we will also prune our tree using cross-validation to see if we are getting the optimal results. So after pruning our tree, that we can see that the relative error bottoms out when the tree is at a size of 7. So this is where this is the size to which we will be pruning our tree. So we have the prune tree over here. Looks like our tree is still using the person of kids born to parents who were never married as the feature to split by. But in terms of model accuracy, once we use this model to predict on our test data set, we are seeing that the model accuracy is pretty low. And more often than not, trees actually do not give a very good prediction error. Therefore, we'll continue to build out random forest models, which tend to outperform trees and decision trees in terms of predictions and misclassification errors. Random forests, what they do is they build lots of trees and average them to reduce the variance of our bushy trees. They can be used for classification or regression. They can deal with a large number of features and are generally successful because they provide a good predictive performance and low incidence of overfitting. And they're also easy to interpret. In creating the best random forest model, we want to minimize the out-of-bag error rate by finding the optimal number of variables selected at each split. So we're going to do that over here. We're building our random forest model. And then we have our plot here, which gives you the difference between the out-of-bag error rate versus our test error rate when we use it to predict on our test set. Ideally, they should line up, but we're seeing that in this case, the test error rate, so this is the line in blue, seems to be higher than our out-of-bag error rate. So the graph over here also shows the importance of the variables used to predict the violent crimes per population. And it seems like, once again, we are seeing that the percentage of kids born to parents who are never married is the most important variable to use in this case.
So, quick summary of all the models that we have used and their performance. So we have used, between linear regression, non-linear regression, and trees and boosting, we have used close to 10 models. And if you look at the comparative of these models, I think the Ridge, Lasso, ElasticNet, all the linear regression models have close to 65% of R-square value with a low RMSE value, and also the non-linear regression models, NeuralNet, KNN, SVM, and Mars, they were also kind of performed at the same level with 64% of R-square. Between the trees and boosting model, I think the XGBoost performed at a 63.8% of R-square. And if you look at the random forest, it has a 65.2% of the variance, explained variance, and a pretty low mean square residual error of 0.019. So all these models performed pretty well, but if we have to look at purely based on R-square, Ridge regression model definitely performs slightly better. So just to conclude our work, I think we live in a society today where the increasing number of crimes, violent crimes in our society is definitely a huge cause of concern, and we should definitely try to analyze data and look at large number of data points and factors to determine what relationship exists between such variables and factors, which could be socioeconomic factors, demographic factors that contribute towards occurrence of such high crime rate rate in society, and the data-driven approach, I think, is paramount to plan for a better tomorrow, a better society. So if we this particular data set that we chose, I think it provides an excellent opportunity to look at a variety of such factors that influence the crime. And for example, we saw like marriage is one of the social constructs that is a huge factor behind such high crime rate. Successful marriages, we definitely saw contribute to healthy development of children, who in turn become more responsible citizen. Also, kids were born to people who are never married, living in dense areas with no schooling, almost no schooling opportunities available, tend to exhibit higher violent crime rate. Also, the models definitely point to some racial factors also. We believe that this is more to do with relatively poor economic conditions in which the African Americans live in our society today compared to those of Caucasian background. And we feel like there is a lot more that needs to happen. Powered by data, there could be more complex AI machine learning models, like variety of neural networks that can be built to make a more accurate prediction of such violent crime rates, which may contribute towards prevention of such crime and make our society a much better place to live for us and our future generation. Thank you so much.